Hi guys, again welcome back to New Electronics World. Let's talk about line code types. That is, various line codes are there. Of this, we will be discussing about the 8 types of line codes. Okay, first one is unipolar non-return to zero, that we will denote as unipolar in our set. Unipolar return to zero, polar non-return to zero and return to zero, bipolar or alternate Mach inverse, that is represented as AMI, then polar quaternary, Manchester coding, and at last differential Manchester coding. Okay, all these are the various line codes. Okay, at first let's discuss about unipolar non-return to zero. Okay, I have not included anything in the slide. Let's draw that first of all. That then only we will be understanding what is it mean unipolar non-return to zero. Okay. Yes, I'll draw this unipolar non-return to zero. First of all, graph is drawn. Okay. Let's draw x and y axis. Then I think it will be drawn like yes 1, then 0 and then 1. Okay, 1 0 1. This is the graph. Okay, I'm not explaining much. I'm just using only 3 letters here, that is 1 0 and 1. Sorry, only 3 bits I'm using. This is unipolar non-return to zero. Okay, I'll write it here. Unipolar N or Z. Okay, yes. Okay, here we can see that only 0 and 1 is used. Let this equal to 0 and this amplitude of this particular one is equal to A. Then what we can say? Yes, this x of t. Yes, this is x of, sorry, this is y of t. Am I right? This is y of, sorry, this is x of t. So this is y axis and this is x of t. This x of t and this is t. Okay, this is x of t and this is t. Then what happens is, what is x of t? X of t is A when it is, this graph shows that the amplitude is A if the bit we have to represent is 1, or we can say that if the time interval, this is the time interval. Okay, this is the time interval TB. So what we can say is the amplitude is A if T is in between 0 and TB. That is, if the time interval is TB, then for 1 the amplitude is A and for 0 the amplitude is 0. Nothing else. What about unipolar return to 0? Unipolar return to 0. I'll draw the graph here. For unipolar return to 0, similar graph is here, but a small difference is there. Use another color to show the line. Okay. The time period we'll use here is again TB. Then only you will be understanding what I'm telling. Yes, the time interval is TB. This topic is very much important, so that you have to keep more interest on this. Okay, so I'm talking in very simple manner. For an LKG student, this can be understood. This is unipolar return to zero. This question has been asked in the previous years many times. Okay, Yes. Then how can we represent? How can we represent the ones and zeros? The data that we have to send is again 1. Then how can we represent in unipolar return to 0 format? The 1 can be represented, oh my god, I'll take another color to understand. Yes, then only it will be distinguished. Yes, is 1. Okay, this is the 1 here. Okay, that is for TB by 2. Till TB by 2, the amplitude will be A. The amplitude will be A. I forgot to write this here. Amplitude is A till TB by 2. This is TB, then this is TB by 2. I'm not drawing this here. There's no space here. This portion is TB by 2. This portion. Okay. This is, write it here. Otherwise, you will forget this. Okay, this portion is TB by 2. Then how can you represent the 0? For 0, you don't have to write or draw anything. Here we have to use 0. So, nothing to draw here. Then, what about 1? Again, we are getting 1. How can we represent 1 here? Yes, it is quite easy. Yes, draw it here. 1. Okay, 1. For only half time duration, there will be a pulse. After that, the pulse will not be there. Okay, only for a half duration of the time period, the pulse will be having the amplitude A. Then only it can be said as 1. For 0, that there will be no amplitude. Okay, is it clear? Yes. Okay, here let's see about polar non-return to 0. I have drawn the axis. Polar non-return to 0, we can say that the amplitude is A for time duration of TB. That is, I will draw this here. If we want to pass 1, then it will be like this is 1. Okay, this is 1. I will write it here. This is 1 and I have to pass 0 and 1. Okay, then only it will be clear. Okay, yes, for 0 we'll be having a negative amplitude. Okay, a negative amplitude will be there for demonstrating 0. And then again 1. How can we draw that? Yes, to upward. That is, let's denote it as minus A, sorry, plus A and minus A. That is, for denoting 1 we use plus A, and for denoting 0 we use a negative amplitude minus A. And this is the time duration TB. Okay, is it clear? This is the time duration TB. Then let's see about the polar return to 0. Similar to the previous case, we can see that for 1 there will be amplitude for up to half time duration, and then for 0, similar to previous case, but for 0 there is small difference. 0 there is negative amplitude. For unipolar case, 0 has no amplitude at all, but in the polar case 0 has negative amplitude and 1 has the amplitude at till the half time duration. So this is again plus A, and this one minus A. Okay, is it clear? Yes. Yes, let's look about Manchester coding. This is very important portion because Manchester coding has been asked in 3 or 4 years previous in the previous question paper. Okay. Yes. For Manchester coding, let the code be 1, 0 and 1. This is a previous code, and another one should be there for explanation. Okay. Then what happens in Manchester coding is only, as in the previous case, we'll be having amplitude only up to the half time duration, and for one we have positive amplitude for half time duration and negative amplitude for dB/2 duration. Okay, then it is 0. Then how can we represent that? First we can see negative amplitude, and then it will be increasing to positive amplitude and then continue at this. Okay, and again what will happen? Okay, let us again one half positive amplitude and other half negative amplitude. If another one comes here, what happens is one half positive amplitude, another half negative amplitude. Then if 0 come here, what happens is again comes here and goes here and goes here. Okay, that's what happens. Okay, this thing not needed. Okay, this much is needed. Okay, then what about differential Manchester coding? For differential Manchester coding, we can see 1 at positive half duration as similar to the Manchester coding. Then 0 will be starting from the opposite from where we have stopped. This 0 will be denoted as like here. Okay, this will be 0, and again we have 1. What will we do? We'll continue from the previous state. Okay, continue from the previous state. Then that is from the last level we will continue from in the next state in the case of 1, and for 0 we will go to the opposite side and will continue from there. Okay, and next we got 1, so we have continued from the 0 itself. And if we get again 1, what happens is we will be continuing from where we have stopped. From this portion we will go to down, and if a 0 comes here, what happens is here it will be a break, and 0 will be starting from this point and will be going. And that is what happens when differential Manchester coding is done. This is 0 and this is 1. That's the case. 1 will be continuing from the previous state, and the pulse duration will be half positive and half negative magnitude or amplitude. Okay, for 0 the pulse duration will be half positive and half negative amplitude, but the 0 will be started from the just opposite side of the or opposite level or axis or the or amplitude of the pulse. Okay, yes. Now let's see bipolar AMI and polar quaternary signal. Okay, we can take the previous example 1 0 1. Okay, so what's about bipolar AMI? For bipolar AMI, there will be amplitude A, positive A for denoting 1, and for denoting 0, what will we use is 0. Again 0. And if a 1 again comes, what happens? We will use negative 1. Okay, and if again a 1 comes, it will be going to positive side. Okay, it will be going to positive side because the one will go up and down. In one case it is positive amplitude, then it will be having negative amplitude in the next case. If another one comes here, what happens is it goes to negative amplitude, and if a 0 comes, it will be going 0. Again a 1 comes, it will be going positive. Okay, and so on. Okay, what about polar quaternary? For polar quaternary, what happens is we will use 2 bits. Okay, that is 2 bits means 4 levels will be there. Here we have seen that here A and minus A. Okay, 2 levels are there. So 0, 3 levels were there, but mainly 2 levels were we using. Okay, but in the case of polar quaternary, there will be 4 levels, that is A by 2 minus of A by 2 and minus of A. These all are the 4 levels of polar quaternary. Okay, so let's draw that. Okay, now the color have to be used. Okay, for denoting 1 0, here we have to use some more letters. Okay, 1 0, 1 1, then this is 1, and this is 0, and this is 1. Okay, some more lines have to be drawn here. Then only it will be understandable. Okay, yes. Yes. Okay, here one thing we forgot is for denoting 0 0 we have to use minus A. Then for denoting 0 1 we'll use minus A by 2. Then for denoting 1 0, the next one is 1 0, we will use A by 2. Then A will be used to denote 1 1, that is quaternary, that is we will use 4 levels. Quaternary, that is the word means. Okay, 4 levels are there. So here it comes 1 and 0. These 2 bits will be denoted using a single pulse. Okay, 2 bits will be used used here. So 1 0 means what? A by 2. A by 2 will be the amplitude for 1 0. Then use another color. Let it be. Okay. Then 1 0 1 1. What about 1 1? This will be increasing and will go in A, in the amplitude A. Sorry, not going to. Then again the amplitude is 1 0. 1 0 means here it will come, and another color. Yes, 1 0. It will be going here, and again 1 comes here. Made it, let it be. Sorry, this much is needed. Okay. Okay, we can see here 0 1. I have written as 0 1. So what is 0 1? This minus A by 2. So this will be going down, and this will be continuing as minus A by 2. Okay, that's all. This is about polar quaternary. Okay, I have changed the code here because it is to understand this. Okay, that's all. So I hope all have understood this particular line codes. Okay. Okay, then we can see all we have seen all the type of line codes, that is unipolar non-return to 0, unipolar return to 0, polar non-return to 0 and return to 0, then bipolar AMI, then polar quaternary, and Manchester coding, and at last we have discussed about uh, differential, Manchester coding, all those things we have discussed. And from this you'll be able to write the power spectral density of the line codes. It's very easy. Just write the amplitude for getting 1 and the amplitude for getting zeros for the signal x of t. That is the power spectral density. That denotation is known as power spectral density of the particular line code. And we have discussed about the we haven't discussed about the properties of line code. I think that is very easy, and it should be just by reading the book only you'll be getting the idea of the properties of line codes. I'll just list out the properties, that is bandwidth, then power efficiency, error detection and correction capability, power spectral density, transparency, etc. Okay, these all are the properties of the line codes. I have just listed. No, I have not included that in this PPT, and these all things you have to keep in mind. And line codes are very very important. You have to must study about the line codes, because polar return to 0, non-polar return to 0, and polar return to 0, non-polar return to 0, non-return to 0, unipolar and polar return to 0 as well as non-return to 0. And Manchester coding is very very important and have been asked in previous question papers, so that we have to more concentrate on that portion of the line code. Okay, thank you.